So we're going to start Chapter 3 now, and Chapter 3 covers nuclear radiation. So this first lecture on Chapter 3 is going to be a shorter one, just to introduce you to nuclear radiation. Nuclear radiation sounds really intimidating, it looks really intimidating, but it's actually pretty straightforward. And you might be surprised that you enjoy solving these problems. So, the majority of these problems involving nuclear radiation, simple addition and subtraction, yet it looks much more difficult. So, to get started, we're going to define what nuclear radiation is. And nuclear radiation is when emission or energy is emitted from an atom to become more stable. So these radioactive elements are unstable. So nuclear radiation, the definition is emission of energy from an atom to become more stable. So if you have a radioactive element, it's unstable. So if you find yourself feeling overwhelmed one day and you're feeling a little unstable, like you could emit some radiation, you might call yourself radioactive. So I know I've had those days where I was like, oh my gosh, something's got to give. I've got to emit some energy in order to become more stable. So that's where nuclear radiation comes forth from. It's that these radioactive elements are unstable. They need to become more stable, so they emit energy. So radioactivity is the spontaneous emission of radiation from a nucleus. Now in Chapter 3, I forgot to mention this earlier, that Chapter 3 involves changes in the nucleus. And remember that the nucleus contains the protons and the neutrons. So we're going to see a change in the number of protons and perhaps the number of neutrons. Whereas in Chapter 2 we were talking about electrons and electron arrangement, and that's how the periodic table is arranged. So, kind of start shifting your mindset. Chapter 3 is more with the nucleus, so the protons and the neutrons. Okay, background radiation. We're all exposed to background radiation. This is a low level of radiation from natural and man-made sources to which we are exposed daily. So low level of radiation from natural and man-made sources to which we are exposed daily. Now there are three kinds of radiation that we're going to cover in this course. The first is alpha, and alpha has a mass number of 4 and an atomic number of 2. What's the Greek symbol? Alpha, it's kind of a fish. If you look on your periodic table, the element that has an atomic number of 2 is helium. Another way to write an alpha particle is using the abbreviation for helium, 4 and 2. So helium is charged, it has a +2 charge, and it moves relatively slowly. if you worked with alpha radiation on a daily basis in order to protect yourself from damage from being exposed to this radiation, in other words, shielding, in parentheses, protection. A few sheets of paper would protect you from alpha radiation. Your clothes would actually stop alpha radiation, or your skin. So I'm going to write an example of alpha decay. So you have this radioactive element that's unstable. In order to become more stable, it emits an alpha particle. So just to give you an idea of what these equations will look like, because they look really intimidating at first, they're not bad. They're really a lot of fun. But I might be a little biased. So, okay, so uranium-238-92 decays to produce an alpha particle and thorium-234-90. Now the way these equations work, you can kind of think of that arrow as the equal sign. And so the sum of the mass numbers on the left must equal the sum of the mass numbers on the right. So on this side we have 238. So the sum of the mass numbers here, 234 plus 4, that checks out, 238. So that's balanced. Same thing has to be true of the atomic numbers. So we have 92 on the left, and then 90 plus 2 gives us 92. So that's balanced. So I could have just left this blank and said, fill that in. And with addition and subtraction, you could have figured that out. Okay, so that's alpha radiation. That's the lowest energy form of radiation that we're going to learn about. So the next type of radiation is higher in energy, so you're going to need more shielding, which we'll see in just a second. So beta, the symbol for beta is 0, -1, and it's a Greek symbol for beta. Remember, we have a subatomic particle that has a -1 charge. So the proton, electron, or neutron? The electron, right? The electron has a -1 charge, and it has a 0 mass. So you could either write this symbol beta or E, and that means the same type of radiation. So beta moves faster than alpha. So shielding would be a block of wood or heavy protective clothing. So an example of beta radiation, iodine-131, 2,3 decays, give you xenon and a beta particle. Now again, notice the sums. You have the sum 131 over here, so 131 plus 0, that checks out. So this is balanced. Your atomic number, 53. 54 plus -1 gives you 53. So you can see that the shielding is more, the shielding required for beta radiation is more than alpha. That's because beta radiation has more energy than alpha radiation. Finally, the highest energy radiation, gamma radiation. Gamma has the symbol 0, 0, and it looks like a fish on its head with tails. Now this is the highest energy form of radiation. So remember, on page 13 of your electromagnetic spectrum, that was the highest. Gamma moves at the speed of light. So in order to protect yourself from gamma radiation, you need a block of lead PB several inches thick. So gamma radiation is used in cancer treatment. So if you hear of somebody saying they have to get radiation, it's gamma radiation. What you notice about gamma radiation is that there isn't a change in mass number or atomic number. Yet the state changes, so it goes from an excited state to a lower energy state. So an example of gamma decay, cobalt-60, which is often used in cancer treatments, decays, it gives off a gamma particle, a beta particle, and then you have 60, 28 nickel. And if you add these up, you have 60 on the left, 60 plus 0, gives you 60, and then 27 over here, so that checks out, 60 and 60. And then -1 plus 28 gives you 27, so that checks out. So you put these in order of increasing energy. So increasing energy. You definitely would want to avoid these forms of radiation if possible. But you know, in some cases, your job deals with radiation. For instance, X-ray technicians. And so X-ray technicians wear film that can detect how much radiation they're exposed to, and this film is reviewed each month. And if you've gone over the radiation exposure limits, then you need to stop working around X-rays. Now, X-rays have a little less energy than gamma, but it's also a form of radiation. You know, if you think about when you go to the dentist and you get an X-ray, they put that lead apron on you, so it's very heavy, and that's to protect your reproductive organs. If you're female. So I just completely lost my train of thought. In terms of radiation exposure, one of the ways to reduce your exposure, so to reduce exposure to radiation, one thing you can do is your distance. So if you want to reduce the exposure to radiation, you can increase your distance. And then in terms of time, would you want to increase or decrease the amount of time that you're exposed to this radiation? You want to decrease the amount of time that you're exposed to this radiation. So, you know, if you work with radiation on a daily basis, it's done, you know, all over. I used to work for a radiochemical supplier, and we made radioactively labeled chemicals. And, you know, every Friday we'd all have to take urinalysis. And if we, our numbers came back too high, then we couldn't work in the lab for a week. If they were really high, you couldn't work in the lab for a few months. So actually one time there was a chemist who had inhaled a lot of radioactive, it was carbon-14. It was a very volatile form, and so they couldn't work in the lab for a few months. But these tests are designed to protect the workers. You know, and you know, as long as you're very careful, you wear, you know, gloves, you wear coverings over your clothes so that you don't track radioactivity everywhere. It's It can be done. It's just there are tracking devices that need to be used. So this is going to conclude the first lecture on radioactivity, and the main thing is just to kind of introduce you to these terms alpha, beta, and gamma. Coming up later, we're going to learn how to balance these chemical equations, and you might be able to impress your friends with these fancy numbers and symbols that you write, but it's not that much harder than the examples I showed you today, so it really won't be much more difficult. So I hope you enjoy it. Do the problems, just do the few problems that correspond to nuclear radiation, and that's all for now. Until next time.